Because it's an internal track, right? There's the internal
yeah,
and the external.
and then there are it's called free floating.
Ah.
So now I got from regular to free floating.
Okay, got it. Okay, but you still put the spectroscopy out.
Oh,
you could just.
Yeah, I could just say.
Just say API.
Yeah.
Okay, got it. Okay. Yeah, I remember. I remember because in Stuttgart we had those group leaders, but I hardly remember if they were actually like departments, but it probably depends on what sort of.
Yeah, so you have the independent groups and the subgroups.
Okay.
Oh, but officially the appointment starts in January. So
ah. Wow.
technically
okay.
accurate.
True, because you're still the flat hours. Okay, that's fun. Let's see. How you?
Good.
Good. Okay. Let's see. Maybe we start. Okay. All right. Hello, everyone. Thanks for coming to our condensed matter biophysics sort of seminar series. It's a great pleasure to have Nikita Kavokine here, who actually is now a group leader at the Max Planck Institute of Mainz, so in Germany. So it's a big chance. It's a big honor for us to host you today. Nikita did his undergrad, master, and PhD all at the École Normale Supérieure in Paris, which is one of the top schools in France, and then spent some time, I think it was like sort of a Humboldt fellowship, and then I'm not sure if the Flatiron has its own fellowship at the Flatiron Institute in New York City. And so he's very nearby, and you're still a fellow right now, which is the opportunity we took to invite him over. And it's great to have you here. And he's going to talk about some of the themes I think he did in the past, and he's going to pursue in the future as a group leader now at Max Planck in Mainz, which is on quantum plumbing. So we are very, very honored to have you, and without further ado, the floor is yours. Thank you. Welcome, Nikita.
Thank you very much, Matthias, for the introduction and the invitation. It's a pleasure to be here and to bore you with the subject of plumbing. Now, what's going to make it more interesting is that we'll be looking at plumbing in very small pipes. How small? Well, typically, I'm interested in pipes that are between 1 and 100 nanometers in diameter. So for scale, a water molecule is about 0.3 nanometers across, so that's 3 to 200 water molecules that fit across the tube. And briefly, why would we care about such tiny pipes? Well, they can be found in many different places. For instance, the channels that we have embedded in all of our cells' membranes and that allow for ion and water transport inside and from outside to inside the cell, they have openings on the scale of the salt ions, so typically nanometric. Then if you look at the more industrial scale, well, all the membranes that are used for water desalination or the increasingly popular blue energy harvesting, extracting energy from salinity gradients. Well, these also have nanometric openings on the scale of the salt ions. Now, the approach that has been taken in the field of nanofluidics to understand something about these systems of practical interest is to manufacture some well-controlled devices that can be studied at the single channel level. Well, nanofluidics, in fact, is a relatively young field. It emerged about 20 years ago in the wake of microfluidics. And the first systems people made were these nanopores drilled in silicon-based membranes that had openings on the 10 nanometer, 100 nanometer scale. And going smaller than that was a real technical challenge, and it's only fairly recently, around 2016, that we got to molecular scale confinement in, interestingly, every possible geometry at the same time. In the same year, we got atomic scale 0D nanopores, 1D nanotubes, and 2D nanoslits. But actually, is there anything different happening in these nanoscale systems? Is water flowing through a carbon nanotube really different from water flowing through a garden hose? And the esteemed Navier and Stokes would tell you absolutely not. In fact, the Navier-Stokes equation still applies down to about the 1 nanometer scale. Concretely, this means that you can still define a viscosity down to the 1 nanometer scale, which is not so different from the bulk viscosity for water. However, of course, there is a catch, and as Pauli famously said, the devil made the interfaces. The interfaces matter hugely. At the nanoscale, this is simply a question of surface to volume ratio. If we put numbers here in a 3 centimeter radius carbon hose, 1 in 100 million water molecules are in contact with the actual hose. Now, if you look in a 3 nanometer radius carbon nanotube, 1 in 5 water molecules touch the nanotube surface. And so this is going to result in vastly different boundary conditions for the Navier-Stokes equation, or better said, the smaller the scale, the more precisely you'll need to describe the solid-liquid interface in order to write down the relevant boundary condition at that scale. So at the scale of macroscopic hydrodynamics, and the same still holds down to microfluidic length scales, you typically have a no-slip boundary condition for the fluid flow. The liquid velocity vanishes at the wall. And this results in Poiseuille's law for liquid transport within a channel, this parabolic velocity profile, and Ohm's law for electrolyte transport in solution. Now, if you go to smaller nanofluidic length scales, 100 nanometers or so, well, there you need some more microscopic but still coarse grain parameters, which are typically the surface charge and the hydrodynamic slip length. And there will be a lot more about the slip length later. Anyway, what this gives you is this quite rich physics of coupled ion and fluid transport phenomena. You may have heard about streaming currents, diffusion osmosis, electroosmosis. But these things are still very well described by continuum and mean field theory, the so-called Poisson-Nernst-Planck PNP equations. Now, what I would like to show you is that when you go to the smaller scale of what people call single-digit nanopores or angstrofluidics, well, there you need to consider the solid really at the microscopic level of its electronic properties. And this gives you a general feature for the fluid transport that I call interaction confinement. I'll explain what that is. And this gives you some many-body and even many-body quantum effects in the nanoscale fluid transport. So, what do I mean by this interaction confinement? Well, as the simplest example, consider a point charge. And in vacuum, it produces around itself an electric field that points isotropically away from the point charge. Now, if you put this point charge next to a surface, then these electric field lines are going to be distorted because this charge induces some polarization charges inside the solid surface. And so I say that a charged particle is interaction confined when its Coulomb potential is being significantly screened by a nearby solid surface. And you can already see that this interaction confinement is going to be somehow influenced by volume electronic properties of the solid wall, something like the dielectric function. So now, if we put this particle in between two surfaces, say it's an ion in a channel filled with water, then this interaction confinement corresponds to actual confinement of the electric field lines within the channel. You can think of it as being due to the dielectric contrast between the water of high permittivity and the wall of lower permittivity. And so this results in some effective Coulomb interactions for ions in confinement that can be much stronger than the Coulomb interactions in bulk solution. And this, in fact, gives you a lot of physics of ionic correlations, nonlinear memory effects. This is something I looked at a lot during my PhD. However, what I would like to talk about today is instead what happens to water in this regime of interaction confinement. After all, the water molecules, they have dipole moments, also create electric fields that may experience screening by the solid. So what could be going on there? And in some sense, we can already expect something interesting to be going on because, well, the ion dynamics, they are quite slow diffusive. They will couple only to the static electronic properties of the solid. However, water has some charge fluctuations that are much faster in the terahertz frequency range. And this we may expect to couple to some dynamic electronic properties. And so this is work that I started towards the end of my PhD with Frédéric Bocquet and also Marie-Laure Bocquet. And this is something I'm continuing up till now in my group. So we have a water molecule above a solid surface. What happens is that it creates a polarization charge in here. And formally, this is well described by what's called the surface response function, this G of Q and omega. And so this tells you what is the potential induced by the solid in the upper half space in response to an evanescent wave external potential applied in the lower half space. So now if our water molecule moves parallel to the surface at some velocity v, then this polarization charge in here is going to slightly lag behind. And this leads to a friction force called an electronic friction force that acts on the water molecule. We have the formula here. It's expressed in terms of the imaginary part of the surface response function at the typical frequency of the water motion. And so another way to look at this is that when we have water molecules in this interaction confinement regime, they're being screened by the underlying solid. Well, they are subject to an extra friction force because they create electronic excitations in the solid. This is the surface excitation spectrum of your solid material. So this is in fact an old, well-known effect for a single charged particle or dipole molecule. But can we say anything about a cold, dense slab of water? It turns out that we can, but it's far from trivial. And so before telling you how we go about it, let me explain why we should care. So I mentioned this no-slip boundary condition. The macroscopic scale, typically you assume no flow velocity at all. You have this parabolic velocity profile inside the channel. Now, this is in fact an approximation to the more general Navier partial slip boundary condition, which amounts to saying that the viscous stress at the wall balances the solid liquid friction force, which is taken proportional to the flow velocity at the wall. This proportionality coefficient here, lambda, is what's called the solid liquid friction coefficient. Now, the effect of this boundary condition is to take the parabolic velocity profile and shift it by a constant amount that's called the slip velocity here. And this is expressed as 6b over h times the average no-slip velocity here. H is the width of the channel, and b is the so-called hydrodynamic slip length, viscosity divided by friction coefficient. And this is typically a nanometric length scale between roughly 1 and 100 nanometers. And so what this tells you is that at the macroscopic scale, your garden hose is much bigger than the slip length. You don't care about this correction. No slip is a good approximation. But as soon as you start having nanometric channels, the slip velocity becomes very important, and it can even dominate the velocity profile. And so concretely, if you have your garden hose, the permeability of the garden hose, the amount you have to push to achieve a certain flow rate, depends only on the radius of the garden hose and the viscosity of whatever you're pushing through. Now, if you have a nanoscale garden hose, then the amount you have to push depends on the radius, on the viscosity, and on the amount of friction that there is between your liquid and the hose wall material. So the solid liquid friction is crucial at the nanoscale, and we'd like to be able to say something about how it works. So how does it usually work? How do we usually think about it? Well, the understanding of solid liquid friction up till very recently was that it's completely a question of surface roughness. Basically, what happens is that your water molecules bump into even the microscopic lattice structure of your material, and this transfers momentum from the flow to vibrations of the crystal lattice to the foaming molds. And so now what we're saying is that there is an extra contribution to hydrodynamic friction that we're going to call quantum friction that amounts to the water transferring momentum directly to the solid's electrons. And so how can we compute this quantum friction? Well, this is something really that doesn't go well with usual hydrodynamic formalism. We have to stop thinking about solid surfaces as we do in, say, molecular dynamic simulations as an assembly of balls and sticks, and describe the electron clouds that surround these balls and sticks and how maybe they talk to the water molecules on top. So in fact, we need to do interfacial hydrodynamics much like we would do condensed matter physics. And so for the theory people in the audience, briefly, the way we do that is that we describe water by its fluctuating charge density, and we formally quantize it. We say it's a free Gaussian field, much like a Phonon field. And then from the point of view of the electrons, we have something like an electron-phonon problem. We have a Hamiltonian comprising the water electron and electron-electron Coulomb interactions. Now, this is in principle a well-known problem in condensed matter. However, there is a catch, because in order to have friction, we need a water flow. So this whole thing is out of equilibrium, and we need to solve in this specific non-equilibrium Keldysh framework of perturbation theory. Nevertheless, this can be done, and we can get in the end some closed form results for the solid liquid friction coefficient. And so we find that it splits into two terms: the classical roughness term that we already knew about, and this new quantum contribution. And here you have its analytical expression. So the important part in this formula is that it involves the surface response function of the electronic system, and now also the analogous quantity for water, for the liquid. And so basically this is a friction force that's due to the coupling of charge fluctuations between the liquid and the solid, a sort of dynamic analog of the van der Waals force. And in fact, this type of effect has been predicted for two solids separated by a vacuum gap under the names van der Waals friction or Casimir friction. And here we find that there's actually something similar going on at the solid-liquid interface. And so what type of fluctuations are we talking about? Well, the other important part of the formula is this hyperbolic sign squared in the denominator that cuts off any frequencies above thermal frequencies. So what matters for this friction force is low energy thermal excitations. For the electronic system, if we want to have low energy thermal excitations, then we need to have some free conduction electrons. And then the spectrum, typically we have some incoherent particle-hole part, and then possibly a collective plasma mode, which is the dominant feature, in fact, in the spectrum that I will be mostly talking about in the following. And that's an artistic representation of plasma, sort of wave-like excitation of electrons. For the liquid, say water, we are talking about some molecular scale charge fluctuations that I generically call hydrons, by analogy with phonons. And there is a whole zoology of them: Debye mode, vibration mode. For instance, the hydron mode that matters most for the quantum friction is the Debye mode, that it's fairly low frequency, around 1 terahertz. And so the way this coupling is going to work is that the lower the frequency of your plasma mode, the better, the stronger the quantum friction. And so, well, now you may say, very well, we have derived the quantum correction to hydrodynamic friction, but who cares? Maybe it's just small. Well, actually, we found that it plays a crucial role in the interface between water and carbon-based materials. And in fact, there have been many puzzling experimental results about water flow near carbon surfaces. For instance, it was found that monolayer graphene is much more slippery for water than multilayer graphite in terms of slip length, inversely proportional to the friction coefficient. So slip lengths up to 200 nanometers have been found for water on graphene, while it's only 8 nanometers for water on graphite. Then there have been these experiments looking at water flow in individual multi-wall carbon nanotubes, and these found that the slip length actually increases with decreasing tube radius. The smaller the tube, the more slippery it is. And this was all very puzzling because graphene, graphite, and these relatively large radius, above 10 nanometers here, carbon nanotubes, they have really the same surface, they have the same roughness. So how come they have different friction, and could this possibly be quantum friction? Well, in fact, quite interestingly for us, graphene and graphite have very different plasmon modes, and this can be understood at the simplest level as a question of, sorry, just geometry. So in a single graphene layer, the electrons can only move in the plane of the carbon layer, and this motion is quite fast at around 50 terahertz frequency. But now if you have multiple carbon layers, then the electrons may tunnel in between the layers, and this out-of-plane oscillation is much lower, at around 5 terahertz frequency. So that's why you have more quantum friction for water on graphite than on graphene. And then it turns out that the multiple carbon nanotubes essentially interpolate between the properties of graphene and graphite. This is because the interlayer coupling in these tubes depends on the tube radius. So the larger tubes have locally a graphite-like structure. The layers are well aligned, and the electrons can tunnel in between the layers. You get the graphite-like high quantum friction. And then when the radius becomes smaller, the layers become misaligned and the electrons localize within one layer. You get graphene-like low quantum friction. And this misalignment effect is something that I can incorporate into the theory, and then we can account quite well for the experimental data. So, well, this is a theoretical prediction with its lots of assumptions and approximations. How do we really know this is true? Well, since this proposal, we've had some confirmations from both simulations and experiments that this is actually what might be going on. And I would like to start with the simulations. Because you might say, well, why don't you do some ab initio quantum mechanical simulation and just see all this happening? Why do you need to go into all the theory? Well, in fact, it is impossible to do such a simulation because quantum friction is an effect beyond the Born-Oppenheimer approximation, which relies on the electrons being late with respect to the water. And you cannot do a molecular simulation of a solid liquid system beyond the Born-Oppenheimer approximation. However, what you can do is implement a classical proxy for the quantum electron dynamics. And this is what was done by our colleagues in Cambridge. Yes, here I should say Cambridge, UK. They basically took a graphene lattice and put on every carbon atom a little charge attached by a little spring that's called a Druid oscillator. And then if you look at the charge fluctuations of this thing, it kind of looks like the graphite's low energy plasmon mode. And then they can do just a classical molecular dynamics simulation of water on top of the system. They know the set of response functions, and they can directly measure the solid liquid friction in this simulation. And so here is what they find. This is the friction coefficient versus the frequency of the little Druid oscillators. And the red dots are the simulation results. The dashed line is the quantum friction theory. So in their own words, the excellent agreement between the simulation result and equation 3 provides strong support for the theory of quantum friction outlined in reference 34, well, which is pleasant to read being an author of reference 34, but still we shouldn't get too carried away here, because the simulation tells us nothing about whether we are good at describing the actual electron dynamics. However, once some electron dynamics are given as input, then what this tells us is that our theory is very good at describing their coupling to the water dynamics. So that was the simulation, but now can we see quantum friction at work in an experiment? And essentially, if we want to see something happening at the level of the elementary excitations of the system, then a good idea is to poke it with a laser. And quite interestingly for me, my new colleagues in Mainz, headed by Misha Bonn, are very good at poking stuff with lasers. And so we did an experiment where we had a graphene sample in a cell that could be filled with different kinds of liquids. And there was an optical pump pulse that could heat up the electrons in the graphene nearly instantaneously, and then we could loop at these electrons cool over picosecond time scales with terahertz probe pulses. And so what we get is electron temperature versus time after photoexcitation, and so we can extract the cooling time of the graphene electrons when the graphene is in contact with different liquids and for different initial electron temperatures that are set by the pump valve. And so what we see consistently across the different excitation temperatures is that the electrons cool faster in the presence of water and heavy water. There's an isotope effect here. Than without liquid or in the presence of other liquids. When you put methanol or ethanol, there is almost no effect. And it turns out that this faster electron cooling in the presence of water can be interpreted as a signature of water-graphene quantum friction. So the way this works is that, well, first, if you, I'm going to need to plug this in, sorry. And I can keep talking while I do that. The idea is that when you look at heat transfer or energy transfer, it's practically the same thing as friction or momentum transfer. And this is actually clearest to me thinking about the solid-liquid system in this condensed matter picture of coupling between modes and their elementary excitations. So if you consider just two modes at a certain frequency, one in the solid, one in the liquid, then in the case of friction, well, your liquid is flowing, so because of a kind of Doppler shift, you have more elementary excitations or quasi-particles in the liquid mode. And so then because you have a solid-liquid interaction, these elementary excitations can be transferred between these two modes. Because of the occupation difference, you get a net transfer rate of quasi-particles from the liquid to the solid, and you count the momentum that's being transported by those quasi-particles that gives you the friction. Now, if we're talking about heat transfer, then the solid mode has higher occupation than the liquid mode, just because it's a higher temperature. Then there is a net transfer rate from the solid to the liquid, and then we just count the energy instead of the momentum that's being transported by the quasi-particles. And so, with very similar arguments to the theory of quantum friction, you can derive a theory for the solid-liquid heat transfer that involves, again, this overlap of surface response functions of the solid and the liquid. So if we look at these surface response functions, for graphene in frequency momentum space, we have this plasmon mode that has this characteristic square root dependence, but roughly it exists at a frequency here around 50 millielectron volts. And if we look at the liquids now, their spectra don't depend much on momentum, on the wavelength. So at these 50 millielectron volt frequencies, only water and heavy water have a significant spectral density that corresponds to one specific hydrogen mode, namely the libration mode that corresponds to hindered rotations of the water molecules around their center of mass. And so in this way, we understand that the enhanced heat transfer specific to water is due to this resonance between this particular hydrogen mode and the graphene plasmon mode. And this works quantitatively. So if we compare the electron cooling rate predicted by theory to the experimental one, we reproduce the trend with the different liquids. And for this level of theory, the orders of magnitude in the inverse picosecond range work actually quite well. And also we understand the isotope effect. There is a difference between water and heavy water because there is a slight shift in the frequencies of the libration mode. And so altogether, these experiments contain a signature of the direct interaction between a liquid hydrogen mode and the graphene plasmon mode, which is like the basic mechanistic ingredient of quantum friction. And incidentally, from the theory point of view, we find that electron-electron interactions are crucial for this process. So if I was to do the theory switching off the electron-electron interactions, I would overestimate the Coulomb rate by about a factor of 10. And so from the theory point of view, it means that we cannot use simple Boltzmann equation approaches to handle this problem. We need the full theory. So with this, I hope to have convinced you that, well, there are some quantum effects playing a role in nanoscale fluid transport. And so to be fair, it's not like below a certain confinement, the water dynamics really become quantum. No, the water dynamics remain essentially classical. However, what I'm saying is that they can couple in some non-trivial ways to the electrons in the solid surfaces, and these have some intrinsically quantum behavior. And so, altogether, I think this provides a sort of new principle for manipulating liquid flows at the nanoscale through the electronic properties of the channel walls. I call this officially quantum control of nanoscale flows and officially quantum plumbing. And so, one way of doing quantum plumbing that we have recently been exploring is to couple liquid flows to electronic currents. Now, in fact, if you think about the solid-liquid system in this condensed matter perspective, then it's very natural. Sorry, I've been talking all day. It's very natural that the flow of even a neutral liquid on top of a solid surface should induce an electric current in your solid. Well, this is because quantum friction amounts to direct momentum transfer between the liquid and the solid's electrons. And for now, we have been assuming, well, I haven't told you, but we have been assuming that the electrons relax this momentum infinitely fast. However, they don't have to. In fact, they must accumulate some momentum, and what is electrons that accumulate momentum? That's an electric current. And so, in fact, this tells us that we should have a hydrodynamic Coulomb drag effect, similar to the well-known Coulomb drag effect in condensed matter. Two layers of same-duty material, you flow a current in one, you get the current in the other. And so we have recently observed experimentally such flow-induced electronic currents. So the experiment was done in my former lab in Paris by two PhD students, Mathieu Lisée and Alice Marcotte. So what they have done is that they have used a tuning fork atomic force microscope as a sort of nano fountain pen to deposit a little liquid droplet on top of a multi-layer graphene sample connected to a couple of electrodes here. Then they moved the droplet in between the electrodes and they saw an electric current at the frequency of the water motion. So electric current induced by the flow. Now, an interesting thing in this experiment is that this current depended strongly on the surface state of the sample. We had different ways of making this graphene surface, from atomically smooth to very wrinkled, with folds and wrinkles on the 50 nanometer scale. And so the observation was that the higher the surface roughness as determined by AFM of these samples, the stronger the generated currents. Now, is this surprising at all? Well, actually, this is not entirely surprising, because for a number of years now, people have been seeing different sorts of liquid flow-induced electronic currents. And even there was this experiment a couple of years ago from Wan Lin Guo's group, where they used a similar droplet geometry. And when these experiments have found some explanation, the explanations were, well, in my view, not very exciting, in the sense that in this experiment they said, oh, there are some ions absorbing at the solid-liquid interface, and these just provide the net Coulomb potential that drags the electrons around. However, the key difference between the experiment we did here and, say, this experiment is the scale. This is a millimetric droplet, and this is a micrometric droplet. And so if we take their theoretical model and scale it down to our dimensions, we expect currents in the 10 femtoampere range. And we observed 10 nanoamperes. So there's a 6th order of magnitude problem here. This cannot be it. And so with my student Baptiste Coquinot, we have tried to see, well, could this be this hydrodynamic Coulomb drag? And so, well, it turns out it's all a game of momentum transfer. In quantum plumbing, we deal with momentum leaks. Essentially, if we want to compute Coulomb drag, we need to know how much momentum the electrons accumulate. And this can be pictured as an average drift velocity of the electrons that we call the electronic wind velocity. And this is what skews the Fermi distribution here. And so if we want to compute this electronic wind velocity, then we need to say explicitly how do the electrons relax their momentum. And this is where we need phonons in the picture. The main source of momentum relaxation for the electrons here is the electron-phonon interaction. But then the phonons, they also receive some momentum directly from the liquid due to the classical roughness-based friction, especially on the rougher wrinkled samples. And this is going to result again in some momentum accumulation in the phonon mode. So something we can also represent by an average drift velocity that we call the phonon wind velocity. And this phonon wind can in turn push the electrons. And so that's another competing current generation mechanism that we would call phonon drag. We have Coulomb drag and we have phonon drag. And so, well, to make a long story short, essentially we took this whole coupled system and put it in our non-equilibrium perturbation theory, and in the end we can get a prediction for the flow-induced electronic current that actually agrees quite well with the experimental data. For instance, here what we reproduce is the dependence of the generated current on the electronic density on the graphite sample. However, well, what do we learn physically? What's the mechanism? Do we see Coulomb drag or do we see phonon drag? Now, what the theory tells us is that the phonon wind velocity is actually much faster than the liquid flow velocity. This is because the phonons receive quite a lot of momentum through the classical roughness-based friction, and they relax it relatively slowly through unclapped processes. Now, there's up to a factor 100,000 between the two. Now, the electronic wind velocity that determines the electric current, this is given by a weighted average of the phonon wind velocity and of the liquid flow velocity. And the weights are the respective electron-phonon and electron-hydrogen scattering times that are actually of similar order of magnitude. And so the electronic wind velocity is actually dominated by the phonon contribution. We're seeing mostly phonon drag in this experiment. And that's why we have these surprisingly high electric currents, and that's why it depends on the sample surface state. The larger the wrinkles, the stronger the classical friction, the more momentum we transfer to the phonons. However, this all doesn't mean that the effect of the direct Coulomb interaction between the liquid and the electrons is always negligible. In fact, because of this term here, the electronic velocity is lower in the presence of this interaction than what it would be without it. And this is because in this setting, the electrons relax some of their momentum to the liquid. And this is in fact a far-reaching observation. If the electrons are giving momentum to the liquid, it means that the quantum friction is negative in this instance. Now, how is this possible? We had a perfectly positive quantum friction that explains the difference between graphene and graphite, and now I'm saying it's negative. Well, it's a question of surface roughness and the classical contribution. So when I showed you the experiments with the slip length on graphene and graphite, we were talking about extremely smooth, atomically smooth samples. So there the classical friction is quite small, and the liquid loses most of its momentum through the quantum friction with the electrons, which is positive. And then here we are considering these rough wrinkled samples with very strong classical friction that transfers a lot of momentum to the phonons. And then this excites this phonon wind that goes much faster than the fluid flow, that pushes on the electrons that end up also going faster than the liquid flow. And so the electronic current helps the liquid flow along the surface. The quantum friction is negative. And yeah, so we call this quantum feedback at the solid-liquid interface. And this is also not such a small effect. It can be quite significant. So we can compute this friction reduction due to the negative quantum friction. Of course, the total friction always remains positive. We're not violating the second principle. And so if we look at this quantitatively, well, for graphene at the highest achievable electronic density, this is not huge, but non-negligible. You can get to something like 12% friction reduction. But then graphene is not the ideal system to observe this. If you take a regular 2D electron gas with unit mass at the same electronic density, you can get up to 60% friction reduction through this quantum feedback effect. And so, well, this is some relatively rough theory, but still qualitatively it gives you a rather counterintuitive new principle for making surfaces with reduced hydrodynamic friction. So the idea is to, on the one hand, minimize momentum relaxation in the surface, so less impurities, ideally use a 2D material that cannot transfer momentum too much to the underlying substrate, and then maximize the quantum friction that helps momentum return from the solid to the liquid. And so, well, we're quite excited about these flow-induced electric currents and quantum feedback as a tool for quantum plumbing. Now we have teamed up with the colleagues in Cambridge who do the semi-classical simulations, and they can actually see these flow-induced currents in their simulation. Now, to be precise, they cannot really have an electric current because they have these attached grid particles. So what they see is more like a plasmon wind corresponding to these grid particles. Still, what you can see in these movies is a view from the top, and the blue dots represent the dipole moments of these little grid oscillators. So here, the water is not flowing, and you shouldn't see the blue dots going in any particular direction, while here the water is flowing to the right, and if you look closely, you should see the blue dots going to the right as well. And so while you try to convince yourself that I'm not lying, I'll go to my conclusions, which will be brief. So the main idea I wanted to transmit today is that at the nanoscale, fluid dynamics talk to condensed matter physics. There's really an interface between the two because the hydrodynamic flows and especially fluctuations can talk to the electronic flows and fluctuations. And so with this, we have a new way of controlling liquid flows. At the nanoscale, we can do some quantum plumbing and hopefully engineer nanoscale flows beyond classical limits. And yeah, so plumbing cannot be done without plumbers. And let me advertise open PhD and postdoc positions in both theory and experiment in my group around these topics. And thank you for your attention.
Thank you, Nikita. Very exciting talk. Do we have any questions from the audience? Brad, maybe you start.
This is perhaps a bit of a technical question, but I'm curious about the vertex between your hydron and the electron degrees of freedom. Is that parameterized, or how do you describe it?
Well, in fact, it's quite well fixed by basic physics because it's just a Coulomb interaction. The bare vertex is just a bare Coulomb potential without any screening, and then all the screening in the system is computed self-consistently.
But you're assuming a charge distribution for the water molecule?
So I'm not really assuming, so I have as an input the spectrum of water charge fluctuations, and the only thing I'm saying is that the interaction between a unit charge in water and unit charge in the electronic system is the Coulomb potential, as it should be. So I don't need to assume anything on the microscopic structure of water, and this is not a coarse-grained model, in fact, because in principle, the spectrum that I put in packs all the molecular structure effects down to the smallest scale.
I guess I don't understand. I mean, the unit charge of water is 0, so, but it has a dipole moment.
Well, you don't have to think about molecules. If you just think about, if we forget about the covalent bonds in water, you have an assembly of oxygens and hydrogens.
Yeah.
And, well, because they are bonded, their charge fluctuation spectrum looks in a certain way. But you just think of the water as something that is neutral after averaging in time, but instantaneously you have some charge distribution that fluctuates in some way. We know how it fluctuates because we measure the spectrum. And so when I have a charge that arises somewhere, I know that it interacts with a charge in the solid system through the Coulomb potential. But I don't need to assume anything more than that.
Jay.
So you mentioned the theory is still rough, but do you have can you make a reliable estimate what roughness, atomic roughness, you can expect to have the lowest amount of drag, like in terms of rough?
So the lowest roughness you can get is really atomic scale roughness.
Yeah, but you said from what you are telling me, if I understand correctly, when you increase roughness, you get some of this, quantum effect. So you can reduce friction.
Yeah. So you mean?
So there should be like a minimum, right? Some kind of roughness, you get a minimum amount of drag.
Let me think. Well, I think if you look at the expression, do I have a formula? Yeah. Here, this is the expression for the friction reduction, and this delta lambda is proportional to lambda 0, which is the classical friction coefficient that's dominating the friction. So the relative reduction that you get does not depend on the amount of classical friction, so roughness, that you have. Then possibly if you go to very high friction, at some point you'll start having some non-equilibrium, like far from equilibrium effects beyond the theory, and there you might have some non-trivial dependence.
So you are saying this regime, as long as this equation is more or less out,
yeah,
the reduction is just some certain percentage.
Yeah, so basically your percentage of reduction will start from 0 when you have no roughness, when you just have quantum friction. And then at some point you'll cross over to the regime dominated by classical friction, and then as long as you're dominated by classical friction, the percentage will be fixed by this formula, at least at this level of theory.
Yeah.
I have another question about the diagrammatic expansion. Is there some sense of like which diagrams are the important ones, like RPA or something like that?
Yes, that's a very good question. So indeed what we do is a kind of RPA. So I drew all kinds of diagrams, but we don't actually take into account all of them. So yeah, in the basic quantum friction theory, the only diagrams that we take are these ones. That's kind of an RPA expansion. Then what we also know how to do is to take into account some self-energy diagrams. And this is actually what we do in the theory of the Coulomb drag. You need the self-energy. You need to somehow correct the electron's Green's function compared to the equilibrium one to get an electric current. And that's why we put in the self-energy. And then the vertex corrections, well, for now we say that through some Migdal theorem type argument, they shouldn't really matter. But this is something that I'm doing some numerics now of the quantum Monte Carlo type to see if they do matter or not.
Any other question? Nikita, I'm just wondering on the background, the experiments that you showed, of course, with the carbon nanotubes, which are multi-wall at the time. Right? the argument that they are graphite-like in the large diameter range, is that because all CNTs that are that large are graphitic, meaning AB stack, like Bernal stacking? Because like at the smaller scale, you have chiralities, right?
Yes.
They don't have to have.
They don't.
Yeah.
No. So, this is what I gathered from the nanotube TEM literature from the House group.
Yeah.
Very similar. And my understanding is that indeed at these scales, so 15 nanometers in radius, you don't even call it nanotube anymore. They call it tubules.
Yeah.
And they're really locally graphitized. They have AB and B stacking.
If you had turbostratic graphite, you would think you would recover the very large slip lengths.
Yeah, it should be something more graphene-like. If you can have a piece of turbostratic graphite that's clean enough on the surface.
Sure, of course.
Yeah.
Yeah. Okay. Makes sense. Any other questions? If not, we can thank Nikita again for a very exciting talk. Nikita, stay around. If you have questions, you can come and bother up front here. Okay. Thank you so much, Nikita. Good, how you doing? All right, thank you so much. It's good.
Thank you for the invitation.
Yeah, looking forward to seeing your experiments come about. Because of course, it sounds. I didn't say this, but did you do any experiments with the lyric bouquet actually?
Yeah, I did some.
Okay.
So it's not like the main part of my work. No. I built this fluorescence-based measurement system for the 2D channels.
Ah, okay.
And well, this experiment is a bit of a mess because of these absorption problems. Well, this started when I started my PhD. I had done only experiment before coming to Didrik's lab.
Oh, I didn't realize. Okay.
Yeah, so I did like some microscopy, some physical chemistry stuff. And then I had the bad idea to tell the group, I know how to make confocal microscopes. And he was like, we need a confocal microscope.
Okay.
Well, he was lucky because I built it for 40K and I didn't have to buy one for 400K.
Yeah.
And then the goal was to use this for these fluorescence-based flow measurements. So this started 5 years ago. And still, we have some results. But
fluorescence-based flow, like in vesicles?
No, so the idea is that so these 2D Manchester channels, the idea is to flow calcium through and then detect calcium-induced fluorescence on the outlet.
Okay. Yeah, that makes sense. All right, I didn't realize you built a microscope. That's great. That's a good experience.
Well, that's not much, but at least one thing I'm not so clear about.
That's good. Maybe, let's see. Let me keep up quickly. We have discovered.
No, we didn't. She's. Oh. Oh. What? From 165. Oh, well, they have another time. Oh. Like women love parties. Well, if they did it, we wouldn't.